In section 2.1, we're going to talk about rates of change. The first thing we're going to talk about is what we call an average rate of change. And you know the average rate of change from algebra. The average rate of change is just the slope of a line. And here we're going to deal with special lines. We're going to look at the slope of what we call a secant line. So when we say secant line, what we mean is that this line is going to pass through 2 points. So recall that the slope of a line is going to be the rise over the run, or you look at the change in the y values over the change in the x values. But then the y values in function notation would just be our f of x's. So you look at the change of the function over the change of the x values. So in algebra, we talk about an average rate of change. For example, if you drive 60 miles in 2 hours, your average rate or your speed would be 30 miles per hour. In calculus, we're more interested in what we call the instantaneous rate of change. But first, we're going to look at the average rate of change. So that's just going to be the slope of a secant line. So the secant line is a line that passes through 2 points. And the notation we're going to use is m for slope, and the subscript is sec for secant. In example 1, we're going to consider this graph, f of x equal to negative x squared plus 4x. So we have this parabola that opens down. Now we want to find the average rate of change from x is equal to 1 to x is equal to 2. So this would be our x sub 1 in the formula, and our x sub 2 would be 2. On the graph, we have our x sub 1 and our x sub 2. So we're just going to compute the slope of the line that passes through these 2 points. And that would give us the average rate of change. So remember that this is a secant line. The average rate of change is going to be f of 2 minus f of 1 over 2 minus 1, which is just 4 minus 3 over 1, if I did my math correctly. So that's going to be 4 minus 3 is 1, so 1 over 1, which I would just write as 1. And that would be the average rate of change. It's just the slope of the secant line passing through those 2 points. In the box below this graph, we're going to talk about our instantaneous rate of change. Again, that's our goal in calculus. So going back to driving a car, the average rate of change, or your average speed, is nice. It's what we use to estimate how long we need before we have to arrive someplace on time. But also important is your instantaneous rate of change. You want to know your speed at every instant of your journey to make sure that you're not speeding, because who wants to get a ticket, right? So your speedometer will give you your speed at every instant. So let's say I wanted to figure out the instantaneous rate of change when x is equal to 1. In the graph above, what that would be represented by is by what we call a tangent line. And the instantaneous rate of change is going to be the slope of a tangent line, or m with a subscript tan, at just a single point. So the difference between the secant line and the tangent line is that a tangent line will just pass through one point. Oops, sorry. So above on our graph, that would be our red line. This is our tangent line. Again, this is our goal in calculus, to find slopes of tangent lines. The problem is, if I was to compute the slope of that tangent line, I would get a 0 over 0. Because I just have one point, my x sub 1 and my x sub 2 would be the same. It would be 1. So 0 over 0 is not equal to 0. This is super important in calculus. 0 over 0 is not equal to 0. The slope of that line is clearly not 0. Okay? 0 over 0 is what we call an indeterminate form. Indeterminate means we cannot determine the slope. We have to do something else. Okay, so when we talk about the instantaneous rate of change, it's still going to be a slope. So we're still using the same slope formula. We're using the change in the y values over the change in the x values. The difference is we're looking at the slope formula as our x sub 2 minus x sub 1 gets closer and closer to 0. So what I'm going to do is I'm going to go back up to our graph and show you what that means. Okay? So that just means we're going to take our secant line and we're going to move it closer and closer to our tangent line. So when we compute the slopes of all these secant lines, they're going to be closer and closer to 0 in the denominator. So we'll pick another point that's closer to 1, and we'll compute the secant line passing through these 2 points. And another point, and so on, until we get as close as we can possibly get to our tangent line without our x values being equal, because we don't want the indeterminate form. And then we'll compute the slope of that secant line. And it will be close enough to what the tangent line is, the slope of the tangent line, for us to make a conjecture or a guess on what the slope of that tangent line is. So let's look at example 2. So example 2, we're using the same function that we had in example 1. But here, this is how we compute or make a conjecture about the slope of our tangent line. We start out with slopes of a secant line. Okay? And in this case, we're starting out with x is equal to 2. And we're going to look at x values as they get closer and closer and closer and closer and closer to finally 1.01, which is really close to 1. And we're going to compute the slope of a secant line between 2 and 1. Right? That would be our first one. So if you look at this table, if I put the x value of 2 into my function, I get 4. Okay? And that's what we computed at the top here. Right? So we did f of 2 minus f of 1. So remember, the x values I'm putting in are getting closer and closer to the x value of 1, where I have my tangent line. So if x is equal to 2, the slope of my secant line is 1. We did that in our first example. But as my x values get closer and closer to 1, at 1.8, my f of x is about 3.96, and then my slope turns into about 1.2. So 1.6 gives me an f of x or y value of 3.84, and the slope of that secant line is about 1.4, and so on and so forth. So look at the slopes of these secant lines as my x values get closer and closer to 1. These slopes are getting closer and closer and closer to 2. So my conjecture is that the slope of my tangent line at x is equal to 1 is probably going to be 2. So I would write slope with an M, the subscript TAN, equal to 2. That's my conjecture. Okay. The problem with using these tables is, one, they're tedious. And 2 is, how do you know that you've gotten close enough to 1 to make a correct conjecture? What if the slope is actually 2.1? Should I check 1.001, 1.0001? How far do I go? So this is just a conjecture, just an educated guess based on your table. And in the first few sections of this chapter, we will be computing these slopes of tangent lines with tables. But after these first few sections, we will no longer be using the table because they're just not accurate. Okay, they're good, but we never know if we've gone far enough to make an accurate guess. So we're going to use this part A, where the slope of our tangent line is 2, to write the equation of the line tangent to the curve at the point 1, 3. So remember the equations of your lines. You have two choices. You have the point slope form, which is y minus y sub 1 equal to mx minus x sub 1. Or you can use the y equal to mx plus b. Those are the two forms of equations of lines that we have from algebra. I'm going to use the first form because I have a point, which would be my x sub 1 and my y sub 1. And from part A, I have my slope m. So all I have to do is plug these values in to get y minus 3 equal to 2 times x minus 1. So of course I wouldn't leave it in that form. It's not really simplified. I would get rid of the parentheses and add the 3 to both sides. So this is y minus 3 is equal to 2x minus 2. And then adding the 3 to both sides, I get y is equal to 2x plus 1. So this would be the equation of the line that's tangent to the curve at the point 1, 3. Which means it's that red line. It touches at that 1 point. In part C, it says, without doing any computations, what would be the slope of the line tangent to the curve at x is equal to 2? So I'm going to go back to the graph, and I'm going to look at x is equal to 2. So that would be this red line that I'm drawing. So if you look at that line, it's a horizontal line. So again, going back to algebra, what is the slope of a horizontal line? And here I don't have to do any computations at all. I know that that slope is going to be 0. So the slope of the tangent line is equal to 0. And that would be at the point where x is equal to 2. So on this next page, we're going to do an application of average rate of change, instantaneous rate of change. So the term average rate of change and instantaneous rate of change, that's the general term. But we can also apply this to the velocity of an object. And this is commonly what we use rates of change for. So if we look at the average velocity of an object, we're going to use the notation v for velocity and the subscript av for average. But it's still just the slope of a secant line. It's just another way to say average rate of change. The instantaneous velocity is going to be a v with subscript inst for instant, which is another way to say slope of tangent line. Example 3 says, an arrow is shot straight up into the air. its position from the ground in feet at time t in seconds is given by this position function, s of t equal to negative 16t squared plus 96t plus 5. So we need to fill in the table with the average velocities, then make a conjecture about the instantaneous velocity at t is equal to 1. So what I want you to notice that this is a time interval. 1 comma 2 with the brackets, it's not a point. It's not like an x and a y value, or in this case it would be a t and an s value. Okay? These are t values, and it's a time interval. So it's from t is equal to 1 to t is equal to 2. What we will be computing here is we'll be computing s of 2, because that's where my time interval ends, minus s of 1 over 2 minus 1. So that would be the average velocity, or the slope of the secant line passing through the points. S of 2 is in my calculator. This is clearly a calculator problem. Would be 133. S of 1 is 85. And this is over 1. So this is just 48. So that would be my average velocity, 48. Now the next time interval of t values is 1 to 1.5. So you see our time value went from 2 to 1.5, then we go to, I think the green, 1.1, 1.01, 1.001. So we're getting closer and closer to 1. But remember, we can't reach 1, or else we'll get an indeterminate form. So when we compute s of 1.5 minus s of 1 over 1.5 minus 1. So in my calculator, s of 1.5 should be 113, and you guys check me on my calculations. Minus 85 over 0.5. So I get 56. So remember, I'm trying to see what this average velocity is getting closer and closer and closer to. Oh, do another one. S of 1.1 minus S of 1 over 1.1 minus 1. So S of 1.1 in my calculator, I got 91.24, and I'm not rounding this. You want to not round as much as possible, or your answer will not match the answer on MyMathLab. I got 6.24 over 0.1, which is equal to 62.4. So these values look like they're just getting larger and larger. I hope they start approaching something, or else I won't be able to make a conjecture. I'll have to enter in more values into my table. S of 1.01 minus S of 1 over 1.01 minus 1 is going to be 85.6384 minus 85 over, and this is just going to be 0.01. If you do have to round values, just put in whatever your calculator gives you, and don't round until the final answer, okay? So I'm going to get 0.6384 over the 0.01, and that gives me 63.84. So that's actually good news. The first few values kind of jumped, but now look, I have a 62.4, 63.84. It looks like it's probably getting closer and closer to 64. So let's do the last one and see if that's the pattern. So I'm looking at 1.001. And in my calculator, I get 85.063984. So I'm putting in exactly what my calculator says, minus 85 over 0.001, which is going to be a 0.063984 over 0.001, and that gives me 63.984. So 63.984. It appears from my table that the instantaneous velocity is 64. Okay, so I could check more values. I could do a 1.0001, because how do I know it's not 65? How do I know this is still not going to grow over 64? Well, the answer is I don't. Which is why the tables are a nice method, so you get the basic idea about how we can get closer and closer to something, but they're not really efficient. So my conjecture is that the instantaneous velocity, so v sub inst, is equal to 64. But remember, this problem gave me units, so I have to add units. And the units here are feet per second. So I'm just going to do ft over, and you could do an s, or to be real clear, an sec. So that's 2.1. 2.1 looking at the difference between an average rate of change and an instantaneous rate of change. Going forward, we're going to be concerned with the instantaneous rate of change, and we're going to be looking at more efficient ways to find it rather than making a table. Okay, so that's it.